class is at 9 o'clock. So I will not be taking a very long class today. And did any of you watch that belt trick? This video of the belt trick. Did any of you watch it, or did you try to replicate it? यश, आपने किया क्या?
Yes sir, करके देखा था.
देखा था, अच्छा. Did you try to repeat it yourself?
Yes sir.
Were you successful?
Yes, after second attempt.
After second, okay. Right. Network is being slow for some reason. Okay, so good morning, everybody. Sorry about that. Thank you for coming to the class today. So, in the last, please let me know if my display is not updating. Okay. So in yesterday's lecture, I talked about the transformation properties of a spin 1/2 system. Okay. And the main lesson from that is that how different types of vectors transform under the same symmetry operation, right? So the symmetry operation is the same. It is this rotation. But under the rotation, three-dimensional vectors will transform under the spin 1 representation. Under the three-dimensional representation of the rotation group, two-dimensional vectors will transform under the spin 1/2 representation. So, this fact is important to understand. Now, one of you, Varun, asked me a question, which is so you had shared a problem from Sakurai, that what happens when you act on a state vector with a translation operator. So and whether that situation was similar or the same as when you have these two different senses of rotation on spin 1/2 and spin 1. Now, I just want to emphasize that it's just a different rotation, right? A different representation, right? The symmetry operation is the same. That's the most important thing to keep in mind. So let's see. Okay, so let me just work through this example that Varun has shared with me. And this is from page number 43 of Sakurai. Okay. So the question is the following. I have a translation. T is a translation operator. Okay. So how does T act on, let's say, an eigenstate of the position operator, X? It will just shift it by X plus X prime, right? So what if I take T, the parameter is some small d variation, d of X, and on some general state psi, right? So now what you can do is, here between this operator T and psi, you introduce the identity operator. Okay. Now, and then you use the resolution of identity. So I hope everybody remembers what resolution of identity is. This is one of the most important tools that we use all the time. So you should not forget it. Okay. Okay. We are doing an integral because this is a continuous parameter. So T dx psi equal to T integral dx T dx ket x bra x. Now, in this integral, we have T dx is some fixed parameter, d of x is some fixed parameter, and x is what we are integrating over. It's a dummy variable, right? Now, if you take T of dx and act on the first ket, what do you get? You get x plus dx, x and psi. Okay. So, what is this psi of x? This ket of psi, this just becomes psi of x, right? This is the coefficient of psi along the direction, the eigenstate x. So this is equal to integral of psi of x, x plus dx, dx. But now in this integral, I can perform a change of variables. So from x, I can go to x prime is equal to x plus dx. And then I can write x is equal to x prime minus dx. And because this dx is just some constant parameter, right? So what happens to my integral? I get psi of x become x prime minus dx. X plus dx becomes ket x prime. And yeah, so there is a bit of a notational issue. So let me correct that, because there is a confusion between this. This is a constant shift and this is the differential. Okay, so we don't want both of those to be the same. So instead of this d of x, I'll write delta x. Okay, delta x everywhere. It's important to distinguish this. These two are not the same. Okay. So this is delta x everywhere, delta x. So this becomes psi of x prime minus delta x. And what happens to the differential d of x? It becomes d of x prime, right? If you take this differential, it doesn't change under a constant shift. So this is your shifted wave function, d of right. And so what is the effect of this translation? The effect of this translation is that if you take the translation and act on the eigenstate x, it shifts the eigenstate by plus delta x. But if you take the translation and act on psi of x, okay, under the same translation, psi of x, so this colon means under the effect of this translation, psi of x goes to psi of x minus delta x, right? So this is always what happens whenever you apply a symmetry transformation to any system, right? So as an example, if I write down a vector, some vector in 3 dimensions, for instance, and I write it as v of I, e of I, okay, where I is equal to 1 to 3. Now, e of I are my basis vectors. Right? And v of I are the coefficients of my vector. Okay. Now you apply some symmetry transformation to the system. You have some symmetry transformation which acts on this vector. What is the effect of this symmetry transformation? Under this effect of this symmetry transformation, e of I will go to some e of I prime, right? And this is the symmetry transformation acting on e of I. And v of I, the coefficient, will go to v of I prime, which is S inverse. The inverse, right? So if the basis vector rotates one way, it changes in one sense, and the coefficient has to change in the opposite sense. Okay, this is roughly speaking what is going on. Now, Varun's question was, is this the same as what is happening to the spin 1/2 and spin 1 case? And the answer is no, right? So for spin 1/2 and spin 1, for both we use different representations of SO3, right? For both we use different representations of SO3, right? But right, so it is that is distinct, that is a separate concept from what is happening here. I hope that Varun, this clarifies what you are asking. Varun?
Sir, but I was not asking about this spin, the previous topic about that J vector and LZ vector.
So that's what I'm saying. Na? So in this case, let's say you have a state psi. So if you have the state of a spin 1/2 particle, it will be this. Okay? For spin 1/2. Now how will this state transform? This state will transform under the J is equal to 1/2 state. But if you have the
Sir, not that J, not that matrix J in the previous class. I think you're talking about this small j. I was talking about capital J.
Okay, what about capital J? Which one? Let me see. Previous class meaning the one before yesterday.
Before
right?
the spin, before Christmas.
Before Christmas.
That J. Yeah, you wrote that R changes to R prime as e raised to minus I by h bar.
Right. Okay. This is what you're talking about. Okay. I see. Right. So I might have been mistaken here because again I should be careful. And you're right that if you write the the if you write the state psi, like over here, if you write the state psi as some coefficient psi of r times some state basis vectors, then yeah, the basis vectors will change in one sense. The basis vectors will change with respect to this rotation using this matrix, and psi of this coefficient will change in the opposite sense. So I should have been more careful about this. But the basis vectors, how will you change them? The basis vectors, you will change them using one set of operators, which is these matrix operators, because these are vectors, right? These are the discrete vectors, and the coefficients are continuous functions. This psi of r is a continuous function. So psi of r will change under that continuous operator L of x. L of x, for example, is y dz minus z dy.
Okay, sir.
Okay, I mean, so yeah, your point is well taken, I think. Okay. So maybe I'll come to some explicit example. Maybe probably not today, because today, like I said, I can't take the class cannot run too long, unfortunately. Okay, so yesterday I had said that we would talk about an actual example, right? So this is taken from section 3.2 of Sakurai, and it's the topic of spin precession. Okay, so what is precession? Precession is basically like if you have a spinning top, as an example. If you have a top and you know it's spinning, then what happens? So this top is spinning around its axis, symmetry axis, but it could also be spinning around this other axis, the vertical axis, right? So it can be spinning around the one way, and then it could be going around. So this is basically what happens, you know, with the one way to think of it is, well, it's not the same as orbital motion, I mean, of the Earth, though they might seem similar. So anyway, this is called precession. So now let's ask, so this it happens whenever you put a spin particle with spin in a magnetic field. Okay, so I have a magnetic field, and I'm going to put a particle in this magnetic field. So the question is, I can ask, what is the Hamiltonian of this particle? Okay, so what are the basic components I have? I have a magnetic field. Now this magnetic field again is defined with respect to somebody's lab frame, right? So the components of this magnetic field B, X, Y, Z are defined with respect to some frame of reference. And how do I describe the particle, the spin of the particle? Well, I describe it using the spin operator. Right? Now the spin operator has three components: Sx, Sy, and Sz, right? And what are these? So S of I is equal to h bar by 2 sigma I, where sigma I is the ith polymetric, right? Now the question is, what is the energy of the particle due to the presence of the magnetic field? Okay, so Now, any object which has spin or which has angular momentum, and it's a charged object, right? So if you take a ball which has some charge on the surface, right, and you set this ball in rotation, so it has some angular momentum L, which is not zero. Then what will happen is that this will develop a magnetic dipole moment, right? Why? Because the charges on the surface, due to the rotation of the ball, the charges on the surface will be like currents, constant currents. And when you have a constant current, it creates a magnetic field. So I will write that magnetic field as M, or I'll write it as small b. So a spinning charged particle creates its own magnetic field, right? And this is called the magnetic dipole moment. And let me call this magnetic dipole moment M, right? So this is exactly like, it is analogous to the electric dipole moment. Right? When you have an electric dipole, what happens? I have a plus charge and a minus charge, and I put this in a constant electric field. Okay. So now if I want to write down what is the energy of this system, I get a potential energy term. Okay, ignoring the kinetic energy of the dipole. Now the dipole will also undergo some oscillation, but for the time being, I ignore that. I just ask what is the potential energy. The potential energy would be given as minus P dot E, where P is equal to, this is, let's say, the distance separation between the two charges, and each charge is value Q. This is plus Q and minus Q. So this would be Q times D, the vector D, from minus Q to plus Q. Now, I apologize that I'm moving a little bit without asking you any questions or pauses, because like I said, I have another class at 9. So, but if you have a question, you please ask, okay? Don't wait for me to stop. So in exactly the same way, the potential energy of a magnetic dipole is given by the same kind of expression, which is the dipole moment, magnetic dipole moment, dotted with the external magnetic field. And this minus sign is very important, right? The minus sign tells us that when the dipole moment is aligned with the electric field, so when they are aligned, that is when P dot E is a maximum, right? It's positive, maximum positive value. And that is when the energy of the system is the lowest state, right? So that's why we need to put the minus sign. And similarly, when P dot E is negative, when it is anti-aligned, that is when the energy of the state is maximum, right? So the dipole always wants to align with the electric field, right? But when you take P dot E in this case, you get a negative value, right? So that should correspond to the maximum energy. So that's why you have a minus sign here. Same thing in this case. So the Hamiltonian for our charged particle is this dipole moment dotted with the magnetic field. And the thing is, what is the dipole moment? Well, the dipole moment will be related to the angular momentum, right? And how do you measure the angular momentum of the particle? You measure it using the spin operator. So the dipole moment becomes this coefficient multiplied by the spin operator, or actually, right, by the spin operator dotted with p. But it is better to write this as b dot s, because s is an operator and b is a constant. Does anybody have a question? Shubham, you have a question?
No, sir.
No? Okay. Okay, so what is this expression? And what are these, this thing? This is the charge, right? So the dipole moment will be proportional to the charge. And well, this coefficient, I'll have to go back and look at the derivation to tell you where it comes from. Okay, so I'm not going to do that right now. So if you ask what is this Hamiltonian, this Hamiltonian is, if you look at the explicit form of this Hamiltonian, this b dot s, you get bx sx, by sy plus bz sz. Okay. And what is S of Z X? It's a 2 by 2 matrix, right? S of Y is also a 2 by 2 matrix, right? So what is this Hamiltonian? This Hamiltonian is also a 2 by 2 matrix. So we can write down the explicit form of this 2 by 2 matrix, because we know what the explicit form of this S, X, Y, and Z is, okay? So what is S of Z? S of Z is h bar by 2 sigma Z, that is h bar by 2, 1, 0, 0, minus 1. So what is B of Z times S of Z? It just becomes h bar by 2 bz minus bz. Similarly, what will be what is S of x? H bar by 2 sigma x, 0 h bar by 2, h bar by 2, 0. So B of x sigma x, I'll take the h bar by 2 outside, becomes 0 bx bx 0. Okay. And what about S of y? Same thing. H bar by 2, 0. I always forget. Minus I, 0. It doesn't matter. You can put minus plus. I mean, it's a choice of convention. So H bar by 2, 0 minus I times by, I times by, 0. Right? So if I take the sum of all three of these matrices, if I take B of Z as Z, B of X as B, what will I get? All of these three will combine to give me B dot S, and B dot S will be H bar by 2, okay, and maybe I'll put it here instead. H bar by 2, the diagonal component I get BZ, here I get BX minus IBY, BX plus IBY minus BZ. So this is my explicit form of BS, okay. This is actually something that is useful. It is worth remembering what it is, okay. Okay. Now, if Bx and By are 0, right? So by convention, normally what do we say? We say that the vector B is pointing in the Z direction, right? This is just again a choice which makes our life a little bit simpler. Then what does this B dot S become? It becomes H bar by 2 Bz minus Bz0. And what happens to the Hamiltonian? The Hamiltonian becomes minus E by MC B dot S H bar by 2 and times Bz times sigma Z. So this is our Hamiltonian for what? For a spin half particle in a magnetic field. That is the important thing. Why is it a spin half particle? Because I'm using this spin half representation of angular momentum, right? I'm using these Pauli matrices. So if instead of a spin half particle, I said that, well, no, it's a spin one particle, all right? Then how would you write down the Hamiltonian? You would do it in exactly the same way, but instead of for the spin operator for Sx, Sy, and Sz, instead of using the two-dimensional representation, you would use the three-dimensional representation of the rotation group. So you would have 3 by 3 matrices here, right? So anyway, if I do mention, give this in the quiz or the exam, I will not expect you to remember the form of those matrices. I will expect you to remember the form of the Pauli matrices, okay? That much. Okay. And this can be written as, what is his convention, right? So E times B by MC, you take this E and B and MC and times this H bar by 2 sigma Z. So he writes it as where is the minus sign? I don't know where his minus sign went. Omega times S. Omega is equal to E times B over MC. All right. And what is this omega going to be? This omega is the angular velocity, the rate of precession of the electron in the magnetic field. So what is the picture that we will get? We have this electron. It has some magnetic dipole moment. There is an external magnetic field B. And due to the presence of this external magnetic field, this electron will precess. And the frequency of this precession is omega. Okay. Now, after that, one can do lots of different things. One can look at the time evolution of the state, for instance. So if you ask what is the time evolution, well, you know what the Hamiltonian operator is. So the time evolution operator is given by so the Hamiltonian, if you remember, is the generator of time translations. I mean, I hope that was something that I have mentioned in my previous classes, right? So by evolution, what do we mean? We mean change in time, right? So evolution means that if you have the state psi at a certain time t, what is the state at a later time t plus delta t? So what is this? This is a translation along the time direction. And what is the generator of time translation? It's the Hamiltonian. Okay. And so in this case, setting t naught, the initial time, to 0, you will get minus I by h bar omega times s of z. According to my convention, I would get a plus sign. He's getting minus. Now, this is something you can explicitly evaluate, right? You can take the exponential and work it out, right? What will you get when you take this exponential? You will get, remember, we worked it out yesterday, that if you take minus I theta sigma z, what do you get? You get a matrix which is e to the I theta by 2, 0, 0, e to the minus. Sorry, the minus sign is in the first term. Theta by 2, 0, 0. Right? So our time evolution operator will become e to the minus I. And what is this angle theta going to be? It's going to be omega t. Omega t. Okay. So now we can ask the question, how does the spin expectation value evolve under this Hamiltonian? Okay. So this is the same question. So what does this mean? This means that now we can evaluate the expectation value of the spin operator or of the individual components of the spin operator, right? And this will be some function of time. Now, can somebody tell me how do I calculate the time evolution of an operator? So first I need to calculate the time evolution of the operator, right?
Yes, sir.
Do I
Equal
need-
to 1 by iota h cut expectation value of operator comma Hamiltonian.
Good. So that would be right. That would be the dsx by dt. Okay. So the rate of
Yes,
change
sir.
of this operator with respect to time would be given by I by h bar
Is h comma sx plus
right plus some, if you have some explicit change in this operator, right? Now normally we don't have this, so we ignore it. Okay. So this is the time evolution. Now if I solve this equation, what do I get? I get the following, right? Sx of t is equal to u of t Sx at t naught, right? So I start at the time t naught, and then I evolve the operator to the time t, right? This is how I write down the time evolved operator, right? What is this representation called, by the way? Anybody? When I evolve the operator in this manner, what is this representation called? Yash?
Heisenberg.
It's called the Heisenberg representation. In this representation, what happens to the state? Does the state evolve as a function of time? Shubham? Shantanu? Vipul? Anybody? What happens to the state? Does the state change as a function of time in the Heisenberg representation?
State won't change, the operator become time dependent.
You're right. So psi of t will be equal to psi of t naught. So what is the expectation value of Sx as a function of time? It's whatever your state is, and the state remains fixed. Keep that in mind. Times Sx of t times psi. Okay. So these are all very basic things. I mean, these things you should know like off the top of your head. Okay. So in this way, we can calculate this psi of s, this thing. So I'll leave that as a homework problem for you. Which homework set? I think homework number 7, right? Is calculate this s of xt, s of yt, s of zt for this Hamiltonian. So for this Hamiltonian, I have already given you the time evolution operator. Okay, and you can take the initial state to be anything. You can just take this psi to be. It doesn't matter. You can take it to be some arbitrary state alpha beta. Okay. So then let's see 3.289. Right. And then what you can do is you can write the evolution. So calculate it. Let's see what you get. Okay. So this is what describes the time evolution of a spin particle in a magnetic field. Okay. Now, how do you detect this kind of a motion? How do you detect this? So let's look at a experimental setup, and that experimental setup, it goes by the name of neutron interferometry. And actually, if you were on campus, there is we have an experiment in the lab called electron spin resonance, which is related to the spin precession only. But anyway, we don't have neutron interferometry, right? So what is this experiment? Let me just share the Sakurai picture with you. It's better than what I will do if I draw. So this is from Sakurai, okay? Right. So you have nearly a beam of thermal neutrons. Okay, monoenergetic beam. Monoenergetic just means that all the neutrons have the same energy. Thermal, well, thermal means that it's a slow moving electrons. It's split into two parts. Path A goes like this, and path B goes like this. Path A always goes through a magnetic field free region. So there is no magnetic field here, and there is a magnetic field over here. So what happens when the state passes through this, when the neutron passes through this magnetic field, what happens? The state of the neutrons passing through this magnetic field undergoes a phase change, right, due to the magnetic field. What is the phase change? It's given by this e to the plus minus I theta by 2. And so what will happen is when both of the beams meet in this region, there will be interference between these neutrons and these neutrons, right? So when you look at the pattern that these neutrons form on the screen, so you have some sort of a screen, neutrons will fall on that, and exactly the same way that when light falls on a surface, it leaves some dots, right? It leaves some marks. Same way the neutron will leave some marks, right? And you will get some sort of interference fringes, right? You will get some bright fringes and some dark fringes. And what will happen is that now I can change this magnetic field. I can tune this magnetic field. So as I tune this magnetic field, what will happen is that this phase angle over here, this thing, it will change as a function, as I tune the magnetic field. And what will happen to the interference pattern? The interference pattern will shift accordingly, right? Because I'm changing the phase of so you have a wave, right? This is a wave. And if I change the path difference, the interference pattern will change. And how will this interference pattern change? It will change according to some cosine of this phase angle. And now you can ask when is the maximum change? The maximum change will be, well, you can calculate it from the rest of this explanation, right? Okay, so I will stop over here today. And I realized today's class was a little bit rushed, which is not normally what I do. But as I told you, I have another class coming up at 9. Okay. But I have time for questions. So are there any questions? Let me see on YouTube any questions. Are there any? No questions on YouTube.
Sir, electrons also revolve around the axis. Spin half particle also revolving.
Yeah, so it is precessing. It is precessing. So the phenomenon is basically exactly the same as the precession of a top in a gravitational field. Okay, so let me show you what happens. If you have a top in a gravitational field, so you have this is a top, okay, Lattu as we call it in North India. This is a Lattu, and I hope you've all played with Lattus growing up. And so it has some angular momentum, right? So this is like the spin angular momentum of the electron. Let me call this
sir.
L. Okay.
Yes, sir.
And now there is a gravitational field. So what will happen? The gravitational field will act. So let's say this is the center of mass. The gravitational field will act downwards like this, right? This is the force due to gravity, right? And there is some angle between this and the symmetry axis of the top. So what will happen? There will be a torque due to this magnetic field around the fixed point, right? The fixed point, this is the fixed point. So there will be a torque which will be given by F times some length r times the sine theta. What is this length L? This length L will be, this will be the length L, right?
Yes.
Now, because of this torque, so by the Newton's equations of motion, we know that the torque is equal to what? Delta L by delta T,
Yes, sir.
right? I'll put a magnitude sign because I have not specified the direction of the vector, right? Now, if you look at the geometry of this picture, so let me look at this picture from on top, okay? The top view. So the top is, the Lattu is over here, okay? And the force and this radius vector, they all lie along this line. So if you ask what is the direction of this torque, the direction of this torque will be in this direction. This will be the direction of your torque, right? So you have, this is the angular momentum of the top initially, but then the top experiences a change in angular momentum delta L due to this torque. And what is the direction of this angular momentum? It is in a direction perpendicular to this L, right, and parallel to the, and perpendicular to the sense of gravity, right? So it lies in this plane. There is a plane which is perpendicular to the gravitational force, and this delta L is in that plane. So what will be the effect? L plus delta L will cause the rotation of this delta L will change, right? Delta L will change under the effect of this delta L to this thing, L plus delta L. And effectively, what does that mean? That means the top has to shift a little bit, right? So I don't know if it's like this, right? So
Yes.
here it has some angular momentum pointing in this direction, and then there is a delta L in this direction. So what will happen? It shifts like this. Oh, sorry, it shifts like this. Then at that point, so it basically goes like this. So this is exactly what happens in the case of a dipole or a electric dipole in an electric field or a magnetic dipole in a magnetic field. Okay.
Yes, sir.
Question. Any questions? Okay, so I'll stop here and we'll meet again tomorrow. And tomorrow's class, I hope I will not rush it like today's class. Okay. But if you have questions, you please ask them on Moodle or on the chat, like Telegram or somewhere else. Okay. And I have to end this class abruptly today because I have to start the next class at 9. All right.
Yes, sir. Thank you, sir.
So sorry about that. Huh? Okay, guys. Bye. See you tomorrow.